What's up, everyone? Buckle up for a new episode of Tech in Check. Let's dive into the basics and complexities of machinery maintenance with engineers Rich Marriage and Tony Planamento. Join us as we meet with guests from the marine and industrial world to learn about the latest technology that keeps your equipment in check and working for you.
Hello, ladies and gentlemen. Welcome back to another episode of Tech and Check. My name is Tony Planamento. I am the technical project supervisor with Advanced Mechanical Enterprises. And joining me today is Les Baker, senior application engineer with FARO Technologies. We're going to be talking today about 3D scanning and tracking. And Les, go ahead and tell the audience a little bit about yourself.
Hi, Tony. Thanks for the intro. In 2007, I joined FARO after having first used the FARO arm in 1997.
Wow.
And coming to the States in 2000. And I've been with FARO ever since and just love my job. I get to meet cool people. I get to see amazing stuff from a manufacturing perspective. It's a real eye-opener. And I get to work with really cool toys.
Yeah. And what primarily do you do with FARO now?
Now at FARO, my job is to train our customers. It's to help out technical demos, to make sure that we can show the customers who are interested in our equipment proof of concept so that they already have a good idea of the return on investment they can get. And I also work with our product management teams, our marketing team, and our engineering team on new products and new
updates.
Yeah, and updates. So it could be software testing, it could be hardware testing. And then I'm also involved in supporting our customers as well. So when application-specific tech support calls come in to our tech support team that may not have had the experience in the field to answer that question, then it can get thrown over towards the application engineering team and they can help customers deliver on their dreams.
Customize those testing plans and procedures to get a good firm deliverable.
Exactly.
Good. So tell me a little bit more about FARO, like the history, how they became to be and what they're...
Well, FARO, the F, the A, the R, and the O, the acronym actually stands for something.
Oh.
So it means Fraser and Rabb Orthopedics.
Oh,
we actually started out as a company that made medical products to make repeatable measurements of difficult things that traditional measurement tools struggle to make. And our founders were Greg Fraser and Simon Rabb. So the Fraser is the F in FARO, and R is and Rabb is the R in FARO. So Fraser and Rabb Orthopedics. They were studying together at McGill University in Montreal and collaborated on their doctorates and developed the first series of products. The company was called ResTech when it was originally founded in 1981, but then it became FARO. And not long after its founding, it actually moved down to Florida to where our headquarters is still in Lake Mary.
Nice. When they were in school, were they going for engineering? Were they dental students, or how did the orthopedics portion come into play?
They were engineers.
Okay.
So the PhDs in engineering, but so not that kind of doctor, not the medical kind of doctor.
You can understand my confusion.
Yeah, exactly. But what they recognized was that the kinds of traditional measurement instruments like calipers and micrometers and things like that, they do really well on things that are flat and square and prismatic.
Yeah.
But if you're trying to measure something that's round or not completely round, it adds a level of complexity to the measurement, and the measurements aren't repeatable.
Yeah.
So 3 people taking 3 measurements each could get 9 different results. So you end up knowing less about the thing you were trying to measure than you thought you knew. So their idea was, instead of using linear encoders, they developed the technique of using rotary encoders so that they could measure angles and translate them into distances.
Okay.
And by their first device, for example, looks a little bit like a torture chair, like an electric chair. But the idea behind it was that the patient would sit in it, and there was a bar that they could move with their knee, and the bar was attached to an encoder, and it would measure the range of motion of the knee. And because the patient's weight was on the chair, there was very little movement as they were operating it, so it gave much more repeatable results. Whereas somebody using a protractor to measure that angle, they could place it in a slightly different position each time. And sorry, you can't see what I'm doing down here, but I'm miming the answer. So that was very unrepeatable. So the new device that they measured was much more repeatable, and they developed the mathematics in order to allow multiple encoders to work together. And by making almost like a robot arm, but manually operated with encoders at each of the rotational points, they could calibrate the position of a tip that was attached to that. So now they could use that to take measurements. And that's how the FARO arm was born.
Ah, okay.
So initially it was used in medical applications, but as the mathematical algorithms became more refined, and as the construction of the devices got better and the bearings got more fluid, the accuracy improved. So it got to the point in the late 90s and the early 2000s where we were able to hold the kind of tolerances that industrial applications would need to hold. Yeah. So it broadened the scope of the arm beyond medical. And now most of our customers come from that industrial sort of sphere rather than
brought you into my world.
Yeah, exactly.
When you're dealing with the size of your hair, thickness of your hair.
Yes. Yeah. 40 microns.
Yeah.
You know, it's pretty tight now.
Now, what's that for Americans? 2000s, right?
Just a
little bit under. Okay. All right. So you talked about the very first product, which is torture chairs.
Yeah.
And then that developed into the first FARO arm, with, developing mathematics and all that stuff. So how did you get into, so that kind of falls more into the 3D tracking side of things, right? The arm.
Yeah, it's contact measurement.
Yeah, contact. Okay. Point. And then how did that technology develop into the FARO tracker, which is what we use predominantly?
Okay, so just to add a little color to what I've already told you about the FARO arm, because I mentioned that I came from another company, and the product that we had developed was a handheld laser scanner that would allow you to scan, I'm going to say small objects, but I've scanned things up to like 45 feet in length with this, with one of these handheld scanners. But basically what it needs is something to tell it where it is in space. so that you can scan with each pass of the scanner as you move around. It knows where it is, so it can build up this 3D object. So that was one of the applications for the FARO arm. And FARO got into scanning very, very early through their provision of what we call a localizer that tells the laser scanner where it is in space. And then they developed their own handheld laser scanners, laser line probes, as they started to become known as, that we could attach to the FARO arm and as a FARO branded complete solution. But the laser tracker actually came about through an acquisition, in that we were working with another company. We covered one part of the market, small scale portable metrology, very, very well, but we didn't really touch the large scale stuff, which the laser tracker did. We worked quite closely with another company called SMX, or the Spatial Metrics Corporation, who developed one of the first laser trackers. And if you think back to 2000, we were going through one of those recessions again. And
.com bubble, right?
Exactly. Exactly. So we were working quite closely together, and we ended up buying that company out, and we incorporated their development team, and the new product that they had been working on was released as the first FARO branded tracker. So they were SMX up to that point, and then FARO took them over and they became the FARO laser tracker.
Okay.
So that gave us the ability to move from measuring things that were within a 12-foot sphere with the size of our arms. And I'm going to do something that I really hate here, which is cross units. And that is the laser trackers at the time had a range of about 30 meters.
Okay.
So
a little under 100 feet, right?
Yeah. So yeah.
So you almost 10 times the range of your capabilities.
So one of the things that we developed as well pretty quickly was the availability of those two devices to work together. The way the laser tracker works is that it basically has two encoders: an azimuth encoder that measures where the laser pointer is tracking around the body, and then there's a zenith encoder that measures the elevation angle that the laser is pointing to.
The side to side, up to down.
Yeah.
Okay.
Basically. And so because it's a laser, it means it's really, 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 really accurate. But because it's a laser, it also doesn't go around corners. It doesn't bend. So it makes it difficult to sometimes measure things that are outside of your line of sight.
Yeah.
So by being able to pair the arm with the tracker can tell the arm where it is in space, and then you can reach around into the hidden stuff and take those measurements.
That's cool. That's really cool. Yeah. I mean, my experience with the tracker has been very line of sight.
Yeah.
Very much so.
And using just the 1.5 inch sphere, or the 7/8 or the 1/2 inch sphere to take measurements that are directly in the line of sight.
Yeah. Do me a favor and remind me how the sphere came about. How did they develop that part of the tracker technology? Has that always been from the beginning, or?
Yeah. Okay. Yeah.
Maybe talk a little bit about what it kind of looks like. Unfortunately, I don't have one in front of me, but
yeah. Well, and the laser tracker was developed really from techniques that were built up through the use of dedicated lasers. So you would have a laser set up that measured a specific distance or a specific feature. That would use maybe a reflective target or a mirror that the laser would measure to. It would be emitted from the laser with a camera viewing the laser, so that you can get the precise point where the tracker hits that target and bounces back into the camera. And the technique that was used to calculate the distance was a thing called a interferometer.
Okay.
And the way an interferometer works is that it measures a specific distance, a known distance, and we know that the laser is traveling at the speed of light.
Yep.
So we know how long it should take it to measure that distance. So if we measure it and it conforms to speed equals distance over time, then you know that the laser device is measuring accurately.
Okay.
So that was awkward because you would have to reposition that laser each time you wanted to measure something different. And you would have to measure that benchmark distance. Then you would have to measure the distance to the target, and it would calculate that distance as a multiple, essentially, of the benchmark distance.
Okay, yeah.
And then you would measure it again to make sure that nothing had changed within the setup, so that you could rely on the result. And you have to do all that without breaking the beam.
Yeah.
Which makes it pretty difficult. And you know the environments that you've worked with this.
Oh, yeah.
Everything in the environment is trying to break your beam, and it becomes painful. So what the early designers of the laser tracker did was that they built a unit that, as I mentioned, has an azimuth axis and a zenith axis, and there are motors in there that drive the laser beam, so that you can point it at a precise location and then measure the distance to that point. So instead of XYZ coordinates that we think of, Cartesian coordinates for placing points in space, what the tracker is actually doing is it's measuring two angles and a distance from the 0, 0, 0 of the tracker.
Advanced trigonometry.
Yeah. It's doing it more quickly than I would be comfortable doing, especially if I didn't have a calculator. But so that's how it's capturing the points in space, and then we can convert them into Cartesian coordinates later.
Okay.
But the way the tracker is able to follow the target is that there is a sensor called a PID sensor that is concentric to the laser emitter.
Okay.
So what happens is that then there are 4 quadrants on this sensor. So the laser shines out, it hits the reflector, and it comes back. And where it hits on the PID sensor operates the motors to try and recenter the laser. So this is happening thousands of times a second, so that you take the target and you can move around and the laser tracker follows you.
Okay. Yeah, I was always actually wondering how it followed the sphere.
Yeah.
So, okay. That's really cool. That's really cool. So it measures something on like a flat surface where the beam hits.
Yeah.
Tells the computer inside the tracker what the X and Y coordinates are of that plane. And then it says, okay, I need you to point over here now.
Yeah.
Wow.
So it basically calculates the offset from the 0, 0, 0 at the center of the PID sensor, and then it just keeps moving to try and keep it centered.
Wow. Very, very fast feedback.
Yeah.
I remember that course in school. That was not a fun class for me. All right. So we were talking a little bit about the sphere now, right? And for those that aren't familiar with it, it's a ball bearing, right?
Yeah.
You've carved 3 triangles essentially into that sphere, right?
Yeah. There are 3 planes, the 3 mutually perpendicular planes that are etched into the center of the ball, or it could be 3 glass mirrors that are positioned relative to the center.
It's kind of like a pyramid, kind of like if you took a pyramid and put it into a sphere. That's what it looks
exactly,
like. Exactly.
Yeah. A negative pyramid.
Yeah.
Yeah.
Okay.
And
so historically, like the original trackers and stuff, were they using the similar reflective technology, or like more of like a flat mirror?
Yeah. Yeah. They have always used this kind of target, which was a divergence from the theodolites and things like that may have been used to do this kind of work before.
Okay.
So the theodolites being the things that you see road workers using at the side of the road to measure distances by projecting angles from multiple locations.
Okay. Yeah, I always wonder what those were.
The old school laser trackers.
Surveying.
Yeah.
Well, that's really cool. So how you mentioned that FARO originally, FARO started with a scanning?
Started
with the tracker.
FARO started with the arm.
Yeah.
And then they acquired SMX.
The tracker.
Yeah.
Yeah.
And that's how we got into laser tracking.
Okay. And then where did scanning come into play?
Again, scanning was another acquisition.
Okay, so that was an acquisition too.
Yeah.
Okay.
Our founders, Greg and Simon, were, they were geeks. They were into technology, and they were always interested in learning the latest and finding out how they could expand our reach.
I can certainly relate to that.
Yeah. And so I think this was back in 2005. We acquired a company in Germany called IQ-Volution, and they had been involved in scanning, long-range scanning, since the very early days.
Okay.
So the first iteration of the scanner that they had a longer range than the laser trackers that we have these days. So the laser tracker, for example, started out at 30 meters, but now we can see all the way out to 80 meters.
Yeah.
At a similar accuracy. The scanners, they started at 100 meters, and now the scanners that we have, depending on model, they can go all the way out to 350 meters.
Wow.
So, you're talking about 1,000-foot radius.
Yeah. That's impressive. That's a lot.
And the scanners have developed, that originally they would just capture point cloud, but then being able to visualize a point cloud that's really, really big is very, very difficult. So very, very quickly, they developed a way of using the camera that captures the point cloud to also visualize the area and then map the pictures onto the point cloud.
Oh, wow.
So now you can see, you're looking at what looks like a picture, but all the points that underline that picture are there, and you can measure essentially from the picture.
Okay.
So over the years, just all of that has just become enhanced. So lighter, faster, stronger. We can scan shiny stuff. We can scan stuff in daylight now, where back in the early days we couldn't. The cameras have gone from black and white to high definition, full color. So everything we've done has been to make life easy for the operator. So one of the things that we pride ourselves on in any of the softwares that we make is that the software always does a lot of the repetitive, heavy lifting that makes somebody's job onerous. So, if there's something that you have to do all the time in order to get started on a job, then we found ways of automating that and building it into the process.
Okay. So walk me through a little bit, kind of more how the scanner works exactly.
So the way the scanner works is that you have a laser that bounces off a right-angled mirror.
Okay.
And that right-angled mirror rotates. So it creates a disc of points.
Okay.
If it hits something within its range, it creates essentially a disc of points. Then it rotates around its azimuth slightly and then does another disc.
Okay.
And rotates and does another disc. So eventually you end up with a spherical point cloud.
All sliced up with discs.
Yeah, which has which replicates the room that you're in.
Okay.
And the more discs you want it to scan, and the more points you want it to capture around the disc, obviously the longer it takes.
Of course. Yeah.
But one of the innovations that we've been involved in is integrating the pictures more with the point clouds using a technology that they call Flash that integrates them at the point of capture so that a scan that used with a high level of detail that used to take maybe 20 or 30 minutes now takes a couple of minutes because of the integration of the different technologies.
Okay. And how do they get that to correlate between the point and the picture?
It doesn't capture a picture per point or per disc. What it does is it scans first, and then once it's finished the scan, the head then rotates and takes a series of photos that matches the sphere that it's taken.
The points that it's already captured. Oh, okay.
So it then uses the XYZ information from the point cloud and the angle information from the camera shots to position them relative to the point cloud.
Okay. When it captures the point clouds, how is it recording that point? Is it the same thing with the tracker where it just reads the bounce back, or how does that work?
Yeah. So what it's doing is that if you imagine that it was white light, there was a point of white light that was shooting out. The light is made up of the spectrum.
Yep.
So you would have violet on one side and red on the other. So ultraviolet to infrared.
Yeah.
On the way out.
Like the Pink Floyd album cover.
Yeah. But we don't have to be on the dark side of the moon.
Okay.
But so the camera is watching the laser go out, and the phase is violet to red, hits the wall, starts to come back, the phase shifts so that now it's reversed.
Okay.
So the camera is essentially measuring the time of flight until the phase shift occurs. And that's how it calculates the distance.
Okay. So it's monitoring color in the spectrum, in the light spectrum, versus reflectivity of the laser beam itself.
Yeah.
Okay.
So it's just capturing that phase shift.
So it's just all done with a camera, basically.
Smoke and mirrors. Light and mirrors.
Light and mirrors. So is this the same as LiDAR, or is it different?
Well, LiDAR is similar, but LiDAR uses light rather than laser, and the which is where the LI in it comes from. We're looking at stuff that's line of sight that you can see that's not obscured, whereas LiDAR can potentially be used to capture things that are obscured.
Okay. Is the laser more accurate than the LiDAR, or is it kind of similar? Just different applications, I guess?
Yeah, it's different applications. It's different. The techniques they're using are very, very similar.
Okay. So it's more application specific.
Yeah.
I understand.
Yeah.
Okay. So that kind of segues nicely into what we want to talk about as kind of the meat of this episode is what are these applications, right? So I guess we could start, we were just talking about the scanner, right? We could talk about some scanner applications. What would be the most common application that you've seen the scanner to start with?
Probably the most common application is in the construction industry, AEC, architecture, engineering, and construction, because they're working with big stuff. They don't necessarily need sub-millimeter accuracy. They just need to know that the door frame is in the right place.
Is it a quarter?
The wall is in the right place. Is the wall flat enough? Is the concrete flat enough within a looser tolerance than a manufacturing tolerance would be?
Okay.
So it allows them to capture data really, really quickly.
Mm-hmm.
So an example of where it's being used these days is, say, for example, this is quite an old building, but say, for example, you wanted to put a new door in to somewhere. You have to be really careful with that first strike of the sledgehammer, because there may be something in there that's not on the blueprint for the building. So one of the things that they do these days is when they've got everything framed out, but before they put the drywall on, they'll scan it so that they know where every stud is, every partition is, every pipe run, every wire run, what have you. Then they can put the drywall up, but they've got a document that says there are wires there, there's water there, there's electricity or phone lines here, so that somebody doesn't do something dumb. So it's made building management much more of a science than an art, like it was before. And it also allows people to keep track of where they are exactly in the construction job. So, again, on TV channels, there are these disaster documentaries about buildings that fell down because nuts and bolts were missed on some of the unions of some of the stanchions. Scanning now takes place at regular intervals to make sure those mistakes don't happen.
That's good.
To make sure that all those bolts are accounted for and what have you.
That's good. That's good.
So, when we're talking about construction, it's not just the construction itself, but for example, you might have a building that you have a car assembly line in, for example, or something similar. So if you wanted to duplicate that, there would be a lot of work involved in trying to do that level of duplication. But what you can do now, for example, and this is true of chemical plants and things like that as well, you could scan an entire chemical plant or an entire automotive assembly line, and there's software that we can use now that can trace all the scans or all the data in the scan that conforms to particular diameters of pipe and the particular pipe fittings that we used to join those pipes. and it can recognize electrical fittings and things like that. There are databases now of all that stuff. So you can essentially build a bill of materials
Just with a scan.
just with the scan of what it would take to create a new version of that plant. And it even goes as far as that you could then use that point cloud that you've captured as a template for a CAD model. And once you've got a CAD model, you can do whatever you like with it.
Yeah.
So maybe the production line goes this way, but you only have space for it to go this way. So you can mirror it.
Yep.
So now it takes a lot less time to duplicate these things that used to take years, or tens of years maybe to bring online.
Wow. That's the most common application, is mostly construction, right? What would you say is the most unique application for the scanning?
Well, it's also used in forensics, for example, and so crime scene investigation. It's used in accident reconstruction and things like that. So, say 10 years ago, if there was a road traffic collision, you could be sat for hours while you're waiting for somebody with a tape measure and to take photos and stuff of the accident scene. These days, most of the state troopers have access to, and a lot of the police forces have access to scanning technology.
Really?
So they can get out there, they can scan everything. That captures the images of the skid marks. So from the point cloud and what have you, they can measure the lengths of the skids from the scans that were taken as a post-process, rather than actually having to document it right there and then before they can open the roads.
Oh, wow.
So and then they can, if they've got something missing, they can come back later. They can scan, and that scan can then be aligned to the previous scan.
Wow.
So that everything matches up.
That's cool. So it's not just for geeks.
No, not at all. And it's gaining more and more use in actually in court cases these days.
Really?
Because somebody might say, I couldn't possibly have hidden the weapon where the prosecution says I hid it because it's just too far. I couldn't throw it there or what have you. So now with the 3D scans, you can create a virtual crime scene for the jury to actually see what happened and how it happened, and they can fly through it and walk through this 3D environment like it's virtual reality.
That's cool.
Whereas before, they would actually have to load the jury onto buses. They would have to take them out to the crime scene with all the logistics and support and what have you that entails, and the delay to the court process as well. So it streamlined things, and it gives people a better overview of the sites that they're talking about. Yeah, I mean,
What's the old phrase? A picture's worth 1,000 words, right?
Exactly. Exactly.
No, that's really interesting. A lot of people that tune in are more adept to the maritime or the industrial aspect. We've touched a little bit on the industrial aspect of things. What would you say would be a good common application for the maritime industry?
Well, the laser tracker, it's fantastically accurate, as you're aware, and it's very, very flexible in the way that it can be used. So, although it may not necessarily be designed for specific applications, the flexibility that it has often lends itself perfectly in specific applications. And one that that really springs to mind is alignments. You know, if a shaft isn't properly aligned and you've got vibration or heat being generated, it all creates problems for the owner of the ship or what have you, or it creates delays, extra maintenance costs, extra fuel costs, because you can't run as quickly as you want to between places. It can actually be a nightmare. So the tracker really lends itself nicely to those kinds of applications. And one of the nice things about it, in comparison to the old school techniques that used to be used, you're actually capturing data that's in the software on the screen, and you're dialing into specific values.
Yeah.
Whereas you're not just hanging a plumb bob from the ceiling and to get the level, you actually have a number, and you can set that level plane wherever you need it. And it just makes it easier and more repeatable.
So yeah, I mean, that brings up a great point. I was actually just doing some internal training for some of our engineers yesterday, and we were measuring a part similar to the part that you guys have for your training up in Lake Mary. And it was actually really cool because I showed them what to do the first time. I measured this part and I saved it as a separate file.
Yeah.
And I basically, they were all there. They were helping me. They were doing all that stuff. And then I said, okay, close that file. And I said, now I need you guys to replicate it. And I think they said that when they finished, their numbers were maybe 1/1000th of an inch different than mine.
Yeah.
So that really speaks to what you're talking about with the repeatability aspect of things across not only multiple measurements, but different people. Yeah. Whereas before you said 3 different people with 3 different measurements, you get 9 different values.
Yeah, exactly. and that's the beauty that the tracker gives you. I mean, just another couple of examples of capabilities that the tracker has. In the head, there's an accelerometer that measures the line that's the force of gravity.
Okay.
If you measure the line that's the force of gravity and you create a plane perpendicular to it, what you have is a perfectly level plane.
Yeah.
And because it's theoretical, it can be perfect. And once you've created that level plane, you can move it to whatever elevation you need it to be. So if, for example, you were trying to set a machine tool perfectly level, you want it to be perfectly level so it runs most economically, so it's not fighting gravity as it runs uphill and downhill, which creates more wear as it accelerates and decelerates because it's not square to gravity. This helps overcome that because you can measure a perfectly level plane. Then you can measure the locations of the mounting feet.
And then
you can shim.
Yep.
You can shim or what have you to
level out the floor, level out the machine,
and now it's running perfectly.
That's really cool.
And as well as leveling it, you can align it as well, so that it is in line with the next machine.
Yeah.
That takes that process.
A lot of our applications that we've been using it is to measure components currently manufactured.
Yeah.
So like, for example, I don't know if you remember, we went down to the Bahamas. There was a tugboat that had run aground.
When you say we, you mean?
AME, I'm sorry. Yeah.
Because I was on standby to help out there. But
yeah, no, you had your bags packed.
No, I trained you guys too well.
Yeah. But yeah, we, my colleague and I went down to the Bahamas. There was a tugboat that ran aground, and they needed to measure various dimensions of those components to determine if they were reusable or salvageable. And yeah, we had to measure the components.
So you're documenting the as found condition,
Exactly.
so you can see if they can be salvaged, reworked, or reverse engineered. So
Exactly.
so that data can be used to create a new version of that, or to see if you can adjust it so that you can make that one work again.
Yeah, exactly. And I don't know if you remember, but I remember speaking with you about this, but the numbers were actually questioned by the manufacturer. And that's what I learned. Something very cool about the tracker is that it has the capability of inducing thermal growth into the machinery. So do me a favor, just walk me through that how to do that again, because that was a really cool feature.
Right.
Of this.
Yeah. Because in the Bahamas, it's hot, it's humid.
Yeah.
So the tracker built into it has temperature sensor, humidity sensor, and pressure sensor. Those are the three parameters you need to know to calculate the density of air. This isn't strictly towards your to what you were saying, but I am going to get there. But so the tracker measures all those things so that it knows how much the beam will bend as it's passing through the air. If the temperature changes, then the density of the air changes, and the laser beam can then diffract more or less. So that is always in play when you're measuring with the laser tracker. So that's why it has its own built-in weather station. But the question that you were asking was that I remember explaining it to you that you were measuring this part and it wasn't exactly 68 degrees Fahrenheit,
something like
20 degrees centigrade. So of course it didn't match the numbers on the print because it was bigger than it should be.
Real quick, because I actually learned this myself during this application. So on a technical schematic drawing, I think you said if it doesn't specify a temperature that the dimensions are specified to, it's 20 C.
Yeah.
And what is that? That's like 68 degrees Fahrenheit. So that was news to me. I never knew that. And I thought that was really interesting. And so, sorry, continue.
So, so, and that was the problem you were seeing, because you were reporting the information back and the manufacturer was going,
it's not possible.
That's not possible. That can't be right. So then we talked about, you found out what material the component was, and you got the temperature, and then we plugged that into the software so it could scale it based on the coefficient of thermal expansion of the material. And then you presented the information back to the customer, who I believe was German, and that made them happy.
Yeah. It was it's very interesting and quite a stressful situation.
But it is what it is.
Yeah. This is what it was measured. And what's interesting is after that happened, it's funny, they actually shipped the components over here to be measured by traditional techniques. And after the measurements were taken with the traditional methods, they found comparable numbers to what we measured over in the Bahamas. So that kind of validated what we found.
Yeah.
And the fact that that thermal condition, that environment, is what was contributing to why they were not to the design spec. So to speak. Okay. So we were talking a little bit about the tracker. I know we were kind of bouncing back and forth with the scanner and everything. Do you feel that there's an application that a scanner could do in the marine industry?
Yeah. I mean, the scanners are becoming more and more used in the marine industry. Let's talk about a construction application that could be applied to the maritime industry. Okay, so you've built a building, and let's say that the floor is not on the concrete slab, but it's raised. It's raised above the concrete slab. So you want to put a wooden floor on above the concrete slab. So you've got all the rooms, all the drywall up, you've got all the joists for the floor and stuff in, and you want to lay the flooring with pre-cut floor panels.
Okay.
And you've got a really tight tolerance on those floor panels, on the fit of them. So traditionally, when you lay the floor panels, you measure the outline right down at the bottom of the wall. But because of the tight tolerance, you know that that's going to be different to where the top of the floor panel is going to intersect the wall. So what you need to know is the size that the floor panel needs to be at the top side.
Yeah.
So you can scan the room. You can use the floor plane, measure a plane on the floor, and then you can offset the plane up by the thickness of the panels.
Okay.
And now you have the exact shape of the wall and the exact dimensions of the wall at that specific site.
It's giving you a profile of the floor in reference to the walls at that height.
Yes.
That's really cool.
So that's an example.
Perfect translation from construction to maritime on that would be like when you're building deck plate frames in an engine room.
Yeah.
Right. So you've got your hull, your shell plating of your hull, right? Obviously you can't build a floor diagonally on your shell plating, right? So you could scan that and then basically raise that plane up to the height of the shell plating.
Yeah.
In order to put your paneling for your deck plates, your deck plate frame.
Yeah.
Okay. That's really cool. That's really interesting. One of our industry partners, I guess I could say would be the right term. They've been asking us when we're going to be ready for doing scanning, because they have applications where they want to scan engine rooms and then lay out where piping can go and how the piping can run in the engine rows. So that's another application that I could think of off the top of my head. And then, I mean, obviously the most common would probably be reverse engineering certain components, right? So I remember I was going through one of the trainings, and the gentleman who was training me, it was not FARO, it was the DesignX software. And he was talking to me about reorienting scans. So like, let's say, if I scan this way, and then I had to stand it up on its end and it's upright this way, you could actually orient this scan to tilt it back down to this scan to complete it.
Yeah.
And what was very interesting, or a thought that popped into my head at that time, was if let's say you've got a component that broke and it's on an antiquated piece of equipment, something that they just don't make anymore, right? You could scan each part of the broken component and say, okay, I want you to align this broken piece to this broken piece. And then it then creates that component into a CAD. And you could 3D print, CNC machine. You could, and now that's the reverse engineering aspect of things, right? Yeah, that's what popped into my head. And I was like, wow, that's really, really interesting. Very applicable.
I mean, you think a lot of the ships that are out there, either naval or merchant vessels, that some of them predate CAD. There's
I've seen some hand drafts.
And if somebody pulls the print, then the revision of the print probably doesn't match the revision of the part that you have. So you can't go off any of that. So reverse engineering it, finding what the as found condition is, and then taking that as the basis to reverse engineer the part is typically the way to go, because then you can repair the stuff that's broken.
Yeah.
You can make that back to nominal, or it may be that if you manufacture it at nominal, it doesn't fit.
Yeah, exactly.
The studs won't go through the bolt pattern. So you then figure out how you need to, we need to remachine this hole slightly larger and off center so that will actually
exactly
work.
Exactly. It's a lot sometimes it's a lot easier to reconfigure the component than the actual structure.
Brute force and ignorance.
Brute force and ignorance. I love that. All right. So that was some really awesome applications. I think there's too many to list in the time we have together. But I would like to ask you one final question before we wrap things up, and that is, where do you see, or where does FARO see itself going in the future? What future products do you see your guys developing?
Well, obviously, I can't talk about specifics, but I would be disappointed if we weren't always working on something. We're a technology company. We need to stay at the forefront of what's going on. So we've always got an eye, obviously, on what's going on around us, and looking closely at what people need to do in order to make it easier for them. So it may be hardware improvements, it may be software improvements, or as you've seen recently with FARO, it's been a combination of the two.
Yeah.
So anything we can do that helps reduce the workload of the guy in the field to guarantee that he's going to walk out with the data that he needs rather than what he thought he wanted. That's our goal, really. It's to take the hard work out of the hard work and improve accuracy, improve efficiency, make the things lighter, faster, stronger, as I've mentioned, because that all helps to make the guy in the field's job easier to do.
Absolutely. So more iterative improvements versus anything paradigm shifting.
Exactly.
Versus what you've already done with this technology.
We're a technology company. As our products have been paradigm shifting, as you said, and if we identify new markets and new ways that we can help people, then potentially there might be a paradigm shifting device coming or software change coming. But for the most part, I think it's evolution. And if you look at the evolution of the product over our lifetime as a company, I think we've made people's lives easier.
I would certainly agree. Well, Les, thank you very much for joining us. Very much appreciate your time. And we look forward to working with you more in the future.
I love the opportunity to hang out with you guys. And, if you need me out in the field again sometime, I'll see you wherever you want me.
Absolutely. Absolutely. All right, ladies and gentlemen, thank you again for tuning in to Tech in Check. I'm Tony Planamento, and we will catch you next time.
Thanks for listening in. We hope you enjoyed our deep dive into this week's tips and tricks for equipment optimization. Want to learn more? Head over to AME's LinkedIn, Facebook, Instagram, or YouTube included in the show notes, along with details from this episode. That's all for now, folks. See you next time.